Fracture mechanics is the field of mechanics concerned with the study of the propagation of cracks in materials. It uses methods of analytical solid mechanics to calculate the driving force on a crack and those of experimental solid mechanics to characterize the material's resistance to fracture. In modern materials science, fracture mechanics is an important tool in improving the mechanical performance of mechanical components. It applies the physics of stress and strain, in particular the theories of elasticity and plasticity, to the microscopic crystallographic defects found in real materials in order to predict the macroscopic mechanical failure of bodies. Fractography is widely used with fracture mechanics to understand the causes of failures and also verify the theoretical failure predictions with real-life failures. The prediction of crack growth is at the heart of the damage tolerance discipline. There are three ways of applying a force to enable a crack to propagate. Mode I fracture, opening mode, Mode 2 fracture, sliding mode, and Mode 3 fracture, tearing mode. Linear elastic fracture mechanics. Griffith's criterion fracture mechanics was developed during World War I by English aeronautical engineer A. Griffith, to explain the failure of brittle materials. Griffith's work was motivated by two contradictory facts. The stress needed to fracture bulk glass is around 100 megapascals. The theoretical stress needed for breaking atomic bonds is approximately 10,000 megapascals. A theory was needed to reconcile these conflicting observations. Also, experiments on glass fibers that Griffith himself conducted suggested that the fracture stress increases as the fiber diameter decreases. Hence the uniaxial tensile strength, which had been used extensively to predict material failure before Griffith, could not be a specimen-independent material property. Griffith suggested that the low fracture strength observed in experiments, as well as the size dependence of strength, was due to the presence of microscopic flaws in the bulk material. To verify the flaw hypothesis, Griffith introduced an artificial flaw in his experimental glass specimens. The artificial flaw was in the form of a surface crack which was much larger than other flaws in a specimen. The experiments showed that the product of the square root of the flaw length and the stress at fracture was nearly constant, which is expressed by the equation. An explanation of this relation in terms of linear elasticity theory is problematic. Linear elasticity theory predicts that stress at the tip of a sharp flaw in a linear elastic material is infinite. To avoid that problem, Griffith developed a thermodynamic approach to explain the relation that he observed. The growth of a crack requires the creation of two new surfaces and hence an increase in the surface energy. Griffith found an expression for the constant C in terms of the surface energy of the crack by solving the elasticity problem of a finite crack in an elastic plate. Briefly, the approach was: compute the potential energy stored in a perfect specimen under a uniaxial tensile load, fix the boundary so that the applied load does no work, and then introduce a crack into the specimen. The crack relaxes the stress and hence reduces the elastic energy near the crack faces. On the other hand, the crack increases the total surface energy of the specimen. Compute the change in the free energy as a function of the crack length. Failure occurs when the free energy attains a peak value at a critical crack length, beyond which the free energy decreases by increasing the crack length, i.e., by causing fracture. Using this procedure, Griffith found that, where E is the Young's modulus of the material and gamma is the surface energy density of the material, assuming E equals 62 gigapascals and gamma equals 1 J per square meter gives excellent agreement of Griffith's predicted fracture stress with experimental results for glass. Irwin's modification. Griffith's work was largely ignored by the engineering community until the early 1950s. The reasons for this appear to be in the actual structural materials. The level of energy needed to cause fracture is orders of magnitude higher than the corresponding surface energy. and in structural materials there are always some inelastic deformations around the crack front that would make the assumption of linear elastic medium with infinite stresses at the crack tip highly unrealistic. Griffith's theory provides excellent agreement with experimental data for brittle materials such as glass. For ductile materials such as steel, though the relation still holds, the surface energy predicted by Griffith's theory is usually unrealistically high. A group working under G.R. Irwin at the U.S. Naval Research Laboratory during World War II realized that plasticity must play a significant role in the fracture of ductile materials. In ductile materials, a plastic zone develops at the tip of the crack. As the applied load increases, the plastic zone increases in size until the crack grows and the material behind the crack tip unloads. The plastic loading and unloading cycle near the crack tip leads to the dissipation of energy as heat. Hence, a dissipative term has to be added to the energy balance relation devised by Griffith for brittle materials. In physical terms, additional energy is needed for crack growth in ductile materials when compared to brittle materials. Irwin's strategy was to partition the energy into two parts: the stored elastic strain energy, which is released as a crack grows. This is the thermodynamic driving force for fracture. The dissipated energy, which includes plastic dissipation, and the surface energy. The dissipated energy provides the thermodynamic resistance to fracture. Then the total energy is, where gamma is the surface energy and Gp is the plastic dissipation per unit area of crack growth. The modified version of Griffith's energy criterion can then be written as for brittle materials such as glass. The surface energy term dominates an. For ductile materials such as steel, the plastic dissipation term dominates an. For polymers close to the glass transition temperature, we have intermediate values of stress intensity factor. Another significant achievement of Irwin and his colleagues was to find a method of calculating the amount of energy available for fracture in terms of the asymptotic stress and displacement fields around a crack front in a linear elastic solid. This asymptotic expression for the stress field around a crack tip is where sigma ij are the Cauchy stresses, r is the distance from the crack tip, theta is the angle with respect to the plane of the crack, and fij are functions that depend on the crack geometry and loading conditions. Irwin called the quantity K the stress intensity factor. Since the quantity Fij is dimensionless, the stress intensity factor can be expressed in units if, when a rigid line inclusion is considered, a similar asymptotic expression for the stress fields is obtained. Strain energy release. Irwin was the first to observe that if the size of the plastic zone around a crack is small compared to the size of the crack, the energy required to grow the crack will not be critically dependent on the state of stress at the crack tip. In other words, a purely elastic solution may be used to calculate the amount of energy available for fracture. The energy release rate for crack growth or strain energy release rate may then be calculated as the change in elastic strain energy per unit area of crack growth, i.e., where U is the elastic energy of the system and A is the crack length. Either the load P or the displacement U can be kept fixed while evaluating the above expressions. Irwin showed that for a mode I crack, the strain energy release rate and the stress intensity factor are related by, where E is the Young's modulus, nu is Poisson's ratio, and K is the stress intensity factor in mode I. Irwin also showed that the strain energy release rate of a planar crack in a linear elastic body can be expressed in terms of the mode I, mode 2, and mode 3 stress intensity factors for the most general loading conditions. Next, Irwin adopted the additional assumption that the size and shape of the energy dissipation zone remains approximately constant during brittle fracture. This assumption suggests that the energy needed to create a unit fracture surface is a constant that depends only on the material. This new material property was given the name fracture toughness and designated GIC. Today, it is the critical stress intensity factor KIC, found in the plane strain condition, which is accepted as the defining property in linear elastic fracture mechanics. Small-scale yielding: when a macroscopic loading is applied to a structure with a crack, the stress near the vicinity of the crack approaches infinity as R0, where R is the distance from the crack tip. As the magnitude of the stress in a material is bounded by the yield stress, there exists a region near the crack tip, of size Rp, in which the material has deformed plastically. The maximum size of this plastic zone can be estimated from the stress intensity factor Kc and the yield stress sigma y, and can be expressed as in this region. The equations of linear elasticity are not valid. Therefore, for linear elastic fracture mechanics to be applicable, 2.5 Rp should be much smaller than the relevant dimensions, such as the length, thickness and width of the structure. This condition, in which the plastic deformation of the structure is confined to a very small region near the crack tip, is commonly referred to as small-scale yielding. Fracture toughness test limitations: but a problem arose for the NRL researchers because naval materials, e.g., shipplate steel, are not perfectly elastic but undergo significant plastic deformation at the tip of a crack. One basic assumption in Irwin's linear elastic fracture mechanics is small-scale yielding, the condition that the size of the plastic zone is small compared to the crack length. However, this assumption is quite restrictive for certain types of failure in structural steels, though such steels can be prone to brittle fracture, which has led to a number of catastrophic failures. Linear elastic fracture mechanics is of limited practical use for structural steels, and fracture toughness testing can be expensive. Elastic plastic fracture mechanics: most engineering materials show some non-linear elastic and inelastic behavior under operating conditions that involve large loads. In such materials, the assumptions of linear elastic fracture mechanics may not hold, that is, the plastic zone at a crack tip may have a size of the same order of magnitude as the crack size. The size and shape of the plastic zone may change as the applied load is increased and also as the crack length increases. Therefore, a more general theory of crack growth is needed for elastic plastic materials that can account for the local conditions for initial crack growth, which include the nucleation, growth, and coalescence of voids or decohesion at a crack tip, a global energy balance criterion for further crack growth and unstable fracture. CTOD. Historically, the first parameter for the determination of fracture toughness in the elastoplastic was the crack tip opening displacement, or opening at the apex of the crack indicated. This parameter was determined by Wells during the studies of structural steels which, due to the high toughness, could not be characterized with the linear elastic fracture mechanics. He noted that before it happened the fracture, the walls of the crack were leaving, and that the crack tip, after fracture, acute to rounded off, is due to plastic deformation. In addition, the rounding of the apex was more pronounced in steels with superior toughness. There are a number of alternative definitions of CTOD. The two most common definitions, CTOD as the displacement at the original crack tip and the 90-degree intercept. The latter definition was suggested by Rice and is commonly used to infer CTOD in finite element measurements. Note that these two definitions are equivalent if the crack blunts in a semicircle. Most laboratory measurements of CTOD have been made on edge-cracked specimens loaded in three-point bending. Early experiments used a flat paddle-shaped gauge that was inserted into the crack. As the crack opened, the paddle gauge rotated, and an electronic signal was sent to an XY plotter. This method was inaccurate, however, because it was difficult to reach the crack tip with the paddle gauge. Today, the displacement V at the crack mouth is measured, and the CTOD is inferred by assuming the specimen halves are rigid and rotate about a hinge point. Our curve. An early attempt in the direction of elastic plastic fracture mechanics was Irwin's crack extension resistance curve, crack growth resistance curve, or R curve. This curve acknowledges the fact that the resistance to fracture increases with growing crack size in elastic plastic materials. The R curve is a plot of the total energy dissipation rate as a function of the crack size and can be used to examine the processes of slow stable crack growth and unstable fracture. However, the R curve was not widely used in applications until the early 1970s. The main reasons appear to be that the R curve depends on the geometry of the specimen and the crack driving force may be difficult to calculate. J integral. In the mid-1960s, James R. Rice and G. P. Cherepanov independently developed a new toughness measure to describe the case where there is sufficient crack tip deformation that the part no longer obeys the linear elastic approximation. Rice's analysis, which assumes nonlinear elastic deformation ahead of the crack tip, is designated the J integral. This analysis is limited to situations where plastic deformation at the crack tip does not extend to the furthest edge of the loaded part. It also demands that the assumed nonlinear elastic behavior of the material is a reasonable approximation in shape and magnitude to the real material's load response. The elastic plastic failure parameter is designated JIC and is conventionally converted to KIC using equation of the appendix to this article. Also note that the J integral approach reduces to the Griffith theory for linear elastic behavior. The mathematical definition of J integral is as follows. Whereas an arbitrary path clockwise around the apex of the crack is the density of strain energy, and the components of the vectors of traction, the components of the displacement vectors, and an incremental length along the path, and another stress and strain tensors. Cohesive zone models when a significant region around a crack tip has undergone plastic deformation. Other approaches can be used to determine the possibility of further crack extension and the direction of crack growth and branching. A simple technique that is easily incorporated into numerical calculations is the cohesive zone model method, which is based on concepts proposed independently by Barenblatt and Dugdale in the early 1960s. The relationship between the Dugdale-Barenblatt models and Griffith's theory was first discussed by Willis in 1967. The equivalence of the two approaches in the context of brittle fracture was shown by Rice in 1968. Interest in cohesive zone modeling of fracture has been reignited since 2000 following the pioneering work on dynamic fracture by Zhu and Needleman, and Camacho and Ortiz. Transition floor size let a material have a yield strength and fracture toughness in mode I. Based on fracture mechanics, the material will fail at stress. Based on plasticity, the material will yield when these curves intersect when. This value of is called as transition floor size, and depends on the material properties of the structure. When the failure is governed by plastic yielding, and when the failure is governed by fracture mechanics. The value for engineering alloys is 100 mm, and for ceramics is 0.001 mm. If we assume that manufacturing processes can give rise to flaws in the order of micrometers, then it can be seen that ceramics are more likely to fail by fracture, whereas engineering alloys would fail by plastic deformation. Crack-type constraint under large-scale yielding. Under small-scale yielding conditions, a single parameter characterizes crack-type conditions and can be used as a geometry-independent fracture criterion. Single-parameter fracture mechanics breaks down in the presence of excessive plasticity, and the fracture toughness depends on the size and geometry of the test specimen. The theories used for large-scale yielding is not very standardized. The following approaches are commonly used among researchers in this field. JQ theory. By using FEM, one can establish a parameter Q to modify the stress field for a better solution when the plastic zone is growing. The new stress field is where for and 0 if not. Q usually takes values from -3 to +2. A negative value greatly changes the geometry of the plastic zone. The JQM theory includes another parameter, the mismatch parameter, which is used for welds to make up for the change in toughness of the weld metal, base metal and heat-affected zone. This value is interpreted to the formula in a similar way as the Q parameter, and the two are usually assumed to be independent of each other. T term effects as an alternative to JQ theory. A parameter T can be used. This only changes the normal stress in the x direction. T does not require the use of FEM, but is derived from constraint. It can be argued that T is limited to LEFM, but as the plastic zone change due to T never reaches the actual crack surface, its validity holds true not only under small-scale yielding. The parameter T also significantly influences on the fracture initiation in brittle materials using maximum tangential strain fracture criterion, as found by the researchers at Texas A&M University. It is found that both parameter T and Poisson's ratio of the material play important roles in prediction of the crack propagation angle and the mixed mode fracture toughness of the materials. Engineering applications. The following information is needed for a fracture mechanics prediction of failure: applied load, residual stress, size and shape of the part, size, shape, location, and orientation of the crack. Usually not all of this information is available and conservative assumptions have to be made. Occasionally post-mortem fracture mechanics analyses are carried out. In the absence of an extreme overload, the causes are either insufficient toughness or an excessively large crack that was not detected during routine inspection.